Okay. Yeah, it was a bit. Yeah. Okay. Good. Let's chat later.
Okay. So welcome everybody to this last session of the conference. In this session, you have two speakers in the field of the string phenomenology. The first speaker is Hans-Peter Niels, and he will speak on the eclectic flavor symmetries from string theory. Okay, Peter, please.
Okay, thank you very much for giving me the opportunity to talk here. I will talk about the question of flavor symmetries as they appear in string theory. So we will discuss the world of flavor from a top-down point of view, and we will see that there are several aspects of flavor symmetry which appear in string theory, something which we call traditional flavor symmetry, and I'll later explain what it is. Modular flavor symmetry. Modular flavor symmetries has become very popular recently because of the work of Ferruglio a few years ago in the bottom-up approach. There will also be a natural appearance of the CP symmetry, and all these three aspects will be covered in this concept of the eclectic flavor symmetry, and it's crucial that you consider all of them. You cannot just have the one without the other. This will lead us to what I call a unified picture of quark and lepton flavor in the sense of localized flavor groups. So we will actually have a possibility to describe quarks and leptons separately. I will then also discuss the question of the top-down versus the bottom-up constructions, at what level we are at the moment. Now, discrete flavor symmetries, of course, have to do with the flavor in the standard model. And of course, most of the parameters in our standard model concern flavor physics, masses and mixing angles of quarks and leptons. So there are many attempts from a bottom-up approach to solve or to understand these mixing angles and masses from the bottom-up perspective with the use of symmetries, discrete symmetries, like the groups I mentioned here and many more. One puzzle in the whole structure, of course, is that flavor symmetries seem to require different models for quark and lepton sector. We have small mixing angles in the quark sector and large mixing angles in the lepton sector. So many of the works which you see in the literature concern either the one or the other, because you seem to have a different picture. Now, flavor symmetries, even if you consider them, they have to be spontaneously broken, and this requires the introduction of fields. They are so-called flavon fields. They have vacuum expectation value, and that leads to the breakdown of flavor symmetry with small parameters creating hierarchies. This bottom-up model building is very successful. There are many models which can fit the measured parameters, but of course, there are maybe too many. There's not one model where one could say, oh, that's the model and that explains everything. So it is actually necessary that we are also thinking about the top-down explanation of flavor, which we'll do here. So such a top-down explanation might come in string theory, and we will, in a certain way, consider the discrete symmetries that appear here. They could come from specific string theory selection rules or symmetries of the compact extra dimension. As an illustration, we consider orbifold compactifications of the heterotic string, as they provide the chiral spectrum of quarks and leptons, so they give us some model which resembles the standard model, and we will also see that there are abundant discrete symmetries as for these for the flavor symmetries. You see, we will here consider these models, which are orbifold compactifications. What is relevant here is that we have compactifications which in some way admit an elliptic vibration, which will be the source of the flavor symmetry. So discrete flavor symmetry. So this is going the wrong direction. So what we will see, so this is in a certain way a summary, which I would want to explain you in the picture, is that we will get traditional flavor symmetry. They are universal in moduli space, and we'll get modular flavor symmetries and a natural candidate for CP, which are non-universal in moduli space. We'll explain that in detail. They unify in this eclectic picture. And in fact, that's the full picture, which allows to exploit also this non-universality in moduli space. It leads to local flavor unification at specific points in moduli space. It allows potentially different pictures for quarks and leptons for that reason. And it also allows a spontaneous breakdown of flavor FCP as a motion in moduli space. So it's the vacuum expectation values of the modulus which plays the role of the flavon field. So let's start with a simple example, flavor from strings. In string theory, we have discrete symmetries. They can arrive from geometry and string selection rules. Let's consider as an example the orbifold T2 over Z3. So we have a two torus, which is defined by these two lattice vectors, which in a certain way identify points. So points that differ by a lattice vector are identified. We then further, so here we have arranged it in such a way that the angle between the lattice vector has 120 degrees. So this allows then a rotation, a mod out by a Z3 group, rotation by 120 degrees. And we also identify points which differ by a rotation of 120 degrees. If we do that, we come to this kind of orbifold, which is the darker shaded region. We have three fixed points of this, modding out with Z3. And the orbifold now will be considered of this region here. You take this point here, which is the same as this point X. You flip it over and you glue it at the edges, and that's the Z3 orbifold. That's the Z3 orbifold. So we have now twisted and untwisted fields. So at the fixed point, we have twisted fields. We have an S3 symmetry from the interchange of the fixed points. And we also have a Z3 times Z3 symmetry from the orbifold selection rules. So what we'll actually get is that we have this multiplicative closure of these groups S3, Z3 times delta 54. Delta 54 is a non-abelian subgroup of SU3. So it could, you see, for example, be used at the flavor symmetry of three families of quarks. The twisted fields form a triplet of delta 54. So this is known since a long time. And also this delta 54 has been used in a lot of bottom-up constructions. But that is, of course, just a try. So, and we have to, in a certain way, be more careful in really making sure that we get the full symmetry group. So we have seen that here we get already a delta 54 is a 54-dimensional symmetry in this simple case. And we have to ask the question, is there more? Or do we have everything? And I think one needs to have a generic way of identifying this picture. And a general mechanism to find the complete set of flavor symmetries is actually given by the outer automorphisms of the Narain space group. So let me just, I cannot explain that in detail because that would be a seminar in itself. Let me first discuss the Narain lattice. The Narain lattice describes the string, and it in a certain way by two vectors, the right movers and the left movers. So in contrast to just a particle where we have just coordinate y for the location, we have here the right movers and the left movers. So if we have d left and d right moving degrees of freedom, the Narain lattice will be given by this will be a 2D torus identified by this situation here, where E is considered the Narain Vielbein matrix. It describes the moduli of the torus, the radii, the angles, and the antisymmetric tensor field. What is important here, you have left and right moving coordinates, so you don't only have the Kaluza-Klein quantum numbers, which you would have in quantum field theory, but you also have the winding numbers, so in a certain way, which are the new aspects in string theory. So now let's try to define the Narain space group. So we have the Narain lattice, and now we further have an orbifold twist on the Narain lattice. So this is now a twist which moves on the left and the right movers, theta r, theta l, which are both elements of SOD, so they are rotations. Let's have a twist of order k, so that theta of k is 1. So for example, in the example we discussed, k was 3. We also consider a symmetric orbifold, so theta L is equal to theta R. In principle, one could also have asymmetric orbifolds, and one could also have off-diagonal elements, which are called roto-translations. Now, the Narain space group is now the group which is generated by the twist theta and the shifts of the Narain lattice. So it's generated by the twists and the shifts in this thing. And this is the group, that's the symmetry. And in fact, it turns out you can show that the outer automorphisms map the group to itself. So the outer automorphisms are the flavour symmetries, the discrete symmetries which you get. Outer automorphisms are, they map the group to itself, but are not elements of the group. And in fact, what we see here is immediately that it also includes modular transformations. These are the transformations which act non-trivially on the winding and momentum space. To do that, let me describe what T-duality and string theory as we know it. That's the interplay of momentum and winding modes. That's the origin of T-duality and string theory. So we interchange simultaneously momentum and winding modes and the radius of, let's take a circle, a radius of the circle to 1 over the radius of the circle. So this transformation maps the theory to its T-dual theory. It's not a symmetry in itself in that point, but it maps a theory to its T-dual, and there's a self-dual point when R squared is alpha prime, which is the string tension, which this is 1 over m string squared. Now, of course, when we consider these models for the generalization of the standard model, M string is very large, and the low energy effective theory describes the momentum states, and the winding states are heavy. So the question is, can T-duality play a relevant role for flavor symmetry? And I will try to show you that the answer is yes. So let's just define duality transformations in SL2 set for what we are actually here on a 2 torus. We consider on a 2 torus. So these are the so-called Möbius transformations SL2, set. And they act on the scalar and the complex structure modulus of the torus. This group is generated by 2 elements, S, T, S with S to the 4 equal to 1 and S squared equal to ST cubed. If we have a modulus, like this complex structure or the scalar modulus, S transforms M to -1 over M. So this is the non-trivial T-duality transformation, which we discussed on the circle earlier. And then we have the T transformation, which gives a shift of the modulus by 1. We will have further transformations which extend actually SL2 set to GL2 set, and they include this transformation of the modulus M to -m bar, where m bar is the complex conjugate. And we will also have mirror symmetry between scalar and complex structure models. That will be the symmetries we have to deal with. Now, when we are thinking about the modulus M, there is a fundamental domain. It lives in the upper half plane in principle, but the fundamental domain of SL2 set will be the dark shaded region here. So everything in the upper half plane can be mapped to this dark shaded region, which of course extends with imaginary part to infinity. So this is the fundamental domain. We will also have to work with modular forms, particle functions which transform under these modular transformation in a given way. So we have the modular group when we have gamma as an element of SL2 set. It acts on the moduli in the following way, that M goes over to AM plus B over CM plus D, where here they are integers because we are working here on the group of the integers, and the determinant of this A, B, C, D is equal to 1. When we have matter fields or other fields in the theory, they typically transform as modular functions of weight k. So they transform under this group gamma as SL2Z. So gamma, rho of gamma will be the representation of that group on a field phi, but that will be not the only transformation. There will be also a prefactor, which is called the automorphy factor, and it in a certain way is given by a number k, which is the power of this prefactor. So then Yukawa couplings will also be modular forms in that theory. They might transform non-trivially under the group, and also even the superpotential could transform non-trivially under group. Only the G, which is the connection of the disconnection of the Kähler potential and the superpotential, has to be invariant under T-duality. So let's go back to the orbifold T2 over Z3. We had already seen that the flavor group before, which we had seen, was delta 54. This is what we call the traditional flavor symmetry because it does not depend on the moduli. Now we have here, we consider the T2 over Z3 orbifold, and we will now see what is the modular flavor symmetry in this case. So here, of course, we have a situation where we have the Z3 orbifold, so the lattice vector have the same length, and the angle between them is frozen to be 120 degrees to allow for this. That means that the U modulus, the complex structure modulus here, is frozen. So the modular transformation which we have now on this object are the ones, they form a subgroup of SL2Z of the Kähler modulus T. Once we have SL2Z, we can construct the mod 3 subgroup gamma 3 of this object of SL2Z. And when we then divide out SL2Z by gamma 3, we get a discrete group, the discrete modular flavor group, which I denote here with gamma 3. So that's gamma 3 here actually is as it acts on the moduli. In fact, we will here have a situation that we get the double cover of gamma 3. So gamma 3 actually is a simple group. It's isomorphic to A4, to the A4 group. We have here the double cover because the twisted states which we have here, they transform in a more complicated way than the moduli. The group or gamma 3 acts on the moduli, but the twisted fields, they in some way have a more general transformation. That's very similar to when you have angular momentum. When you have just even angular momentum, the group is SO3, but when you have spinors, you have the group SU2. In addition, we will have the CP transformation M going to minus M bar here. So the full discrete modular group, which we have here, is known as GL2, 3. This is in a gap notation due to a computer program. This can be written as 48,29. The first entry here, which we usually have, is the number of elements of the group, and the second one is a classification of the group with these elements. So once you know how to handle this program gap, this tells you exactly what the group is. So now we have the symmetries which we had before. We have traditional flavor symmetries. They are universal in moduli space. And so this was the delta 54 before. And then we have modular transformations which act non-trivially on the moduli. Of course, they are not symmetries because the moduli are transformed in a non-trivial way. So the symmetries, the real symmetries which we appear only at specific points in moduli space. At these points, the traditional flavor symmetry is enhanced to a bigger symmetry with some of the modular symmetries. So that is the full flavor symmetry is non-universal in moduli space. And at generic points in moduli space, we have the universal traditional flavor symmetry. Now we come to the notion of the eclectic flavor groups. As I said, we have here delta 54, we have T prime as traditional, and the eclectic flavor group is defined as the multiplicative closure of this group. So here we obtain When we exclude CP, we have a group with 648 elements, which is also known as omega 1. It's the closure of delta 54 T prime. And if we include CP, we have even a group, an eclectic flavour group with 1296 elements. This eclectic group is the largest possible flavour group for a given system. But of course, it's not necessarily linearly realized. The linearly realized amount depends on the position in moduli space. Now, let me discuss a bit more the question of the modular flavor symmetries as they were brought up by Ferruglio in 2017. So we have seen that these modular flavor symmetries appear in string theory, but they had not been used in these bottom-up constructions of flavor till this work. So he, for example, assumed a discrete modular group gamma 3, which you would have here, apart from the fact that at the end we have the double cover T prime. It's isomorphic to A4. And by now there are many more constructions following this work of Ferruglio. This is cited by more than 100 citations even a few months ago. So what you do in bottom-up building, you first take the group, then you assign specific representations to gamma n, and you also have the choice of the modular weights of the matter fields. So this is something which gives you a large amount of freedom in this top-down, in the bottom-up perspective. And we now want to check whether what is the situation in the top-down perspective. Is there UV completion to this kind of actually successful fit? So this the fit of Ferruglio for the lepton sector was very nice with very few parameters. So modular flavor symmetries are in fact quite powerful, especially when we look at the top-down procedure. You see the breakdown, the flavon fields are given by the moduli, at least for the modular flavor symmetry. So we do not have to introduce additional fields. We'll get modular discrete groups, gamma n. We also get the values of the modular fate. They are fixed in string theory in the same way as the representations we'll get for the matter fields. And they are, of course, always accompanied by a traditional flavor symmetry. So you cannot just work with the discrete modular symmetry alone. You also have to include the traditional flavor symmetry because this restricts the couplings in an additional way, which you should not forget. In fact, this whole restrictions which we get here comes from the fact that we have the symmetries of the underlying string theory, which reflects the parameters of the theory, especially also the question of the modular weights. This leads me to when you now want to compare top-down to bottom-up, you have in some way what I call a representation dilemma. In the bottom-up approach, you have the modular flavor group gamma 3. And then we assign, for example, in this model of Ferruglio, a triplet to the left-handed triplet of A4, left-handed leptons and non-trivial singlets, 1, 1 prime and 1 double prime for the right-handed leptons. So you can make a distinction between, and you have a complete freedom of the choice of the modular weights. So you can choose them as you want. Now, when you look, for example, at the top-down approach based here, we have the group T prime. It's the double gamma of gamma 3, but the twisted fields do not transform as a triplet, they transform as a doublet plus a singlet of T prime. There are not many non-trivial singlets in the low energy sector, so this choice might not be possible in a string theory. And also the modular weights are very restricted. They are restricted here to -2/3 and -5/3 and cannot be freely chosen. So in that sense, it still remains to be seen how the top-down and bottom-up approach is consistent, and or whether all of the models, the fits from the bottom approach, really lead to a model which has a UV completion. So where are we at this point? So we have discussed the set 2 free orbifold as it appears in these orbifolds. So you could think of this as an elliptic vibration with a certain twist also in the Calabi-Yau theory. When we start with the torus, we have two moduli, the Kähler modulus T and the complex structure modulus U. So in principle, we would have the full symmetry of the torus here. In the set 3 case, U is frozen, as I had told you, but it still contributes to the eclectic flavor symmetry. And what we'll get here is, in fact, a case for the set 3, which is omega 2 without CP, which is a group of 1944 elements. In the set Q case has also been discussed. There we both have the modulus T and the modulus U. So we have an eclectic group with 2,304 elements. And that is also including CP, you will have 4,608 elements. The next step would be, and that has been done partially already, is that one includes Wilson lines in the picture, even at this level. And this will lead actually to the Siegel modular group SP4, Z, which I'll not discuss here in detail. What I want to discuss now here, in some way, is what we understand with local flavor unification. This was the fundamental domain. The dark shaded region was the fundamental domain of SL2Z. The shaded region here is the fundamental domain of gamma 3. And in addition, we have this CP-like transformation, M going to -1 over M. If we use that, actually the fundamental domain is half again. You can restrict yourself to the fundamental domain of gamma 3, where the real part of M is bigger than 0. So these are the transformations, and these are the fixed points now. So here I give you some points and lines which are fixed under these transformations. Think this point here, 1, 0, is fixed under S. This circle here is fixed under S times U, where U is this transformation M over M bar. These lines here, the red lines, are in a certain way fixed under T and U. U in a certain way reflects at 0 here, and then you can shift back. So we have these non-trivial fixed points here under these various transformations which we have here. And that now translate, when we look at now the modular space of the flavor groups, to bigger groups at these enhanced points in modular space. So delta 54 here is the group throughout moduli space. It's independent of the moduli. When we have, you see, a line or so, a line, we will actually see that the group is enhanced to a group of 108 elements. Typically, this includes a CP transformation, which is this transformation which goes in that direction. If two lines meet, you get actually a group which has 216 elements. And if 3 lines meet here, you get the biggest group in this contact, which is a group with 324 elements. So you have this notion of the groups. Delta 54 is universal in moduli space. At this line, you have a bigger group like S108 element group. And if you go a bit away from this line, this group is spontaneously broken to delta 54. So you could understand that at this line, you have CP unbroken, but when you slightly go away, you break CP in that respect. Now the same we can now discuss in the set 2 orbifold, which is a more complicated because you have 2 unconstrained modulo T and U, and you have to find a way to represent this. You actually take the boundaries of the fundamental domain, you stretch them, and then you have this nice picture of the enhancement of the group. In this case, you will also here, you will have lambda U and lambda T, which are this stretched out boundaries of the fundamental domains. You will also have a line here, which in a certain way is mirror symmetric, where you have T equal to U. So this is a mirror symmetry map between T and U, which is explicitly realized here. The biggest group which you get here, which is linearly realized, is a group with 1152 elements times an R symmetry in Z4. So this is the enhancement of the flavor groups which we get here. So what I tried to explain to you is that in a top-down approach, you see you are led to a unification of the traditional discrete flavor symmetry, CP and modular symmetry. And they are in a huge group, which is called the Eclectic flavor group, which contains all the information, but of course, which is not in principle completely linearly realized. What has to be stressed again, that we had already seen from the Narain Lattice description, that we have left and right movers, that of course modular flavor symmetry is a prediction of string theory. Traditional flavor symmetry as well is a prediction. It's universal in moduli space. They are non-universal enhancements, and so they include CP, and they are broken in generic moduli space. CP is a natural consequence of the symmetries of the underlying string theory. This is an important observation which should be made here. CP seems in string theory to appear naturally. Potential flavor groups are large and non-universal, and you have a spontaneous breakdown as a motion in moduli space. So the consequences, now this opens up a new arena for flavor model building. In the bottom-up picture, this has already partially been done, but typically there has to be ignored that with the typical modular flavor symmetry, you get also a traditional flavor symmetry. In string construction, there are some models which are explicitly constructed, really standard model constructions with 3 families of quarks and leptons. Here they considered something, a 6-dimensional Z3 times Z3 orbifold, which in a 2-dimensional subsector had this Z3, the gamma-free symmetry. So the top-down predicts modular flavor symmetries. There's the concept of local flavor symmetries, and it allows different flavor groups for different sectors of the theory. So here you could, for example, locate quarks and leptons at different points in moduli space, and you get different realization of a flavor group for them. But it's not only the groups which are important when you come from the top down, it's also the representations. So they are clearly restricted, and not all of the possible representation appear. And it remains to be done what are actually the options which we have in the top-down restrictions. And the same, of course, is also true for the modular symmetries. You cannot choose them freely, but you have they are given by string theory. So this brings me to the end of my talk. String theory provides the ingredients for flavor: traditional flavor group, modular flavor group, CP. We also have the modular weights, the automorphic factor, and they in some way reflect the symmetries of the underlying string theory. So we have seen that the eclectic flavor groups provides the basis for flavor, non-universality of flavor symmetry, and allows also different flavor structures for quarks and leptons. Thank you very much.
Okay, thank you. Thank you for a nice and interesting talks. So this is a time for questions and discussions. If you have any questions, then you can raise up your hand or write your question in the chatting window. Well, okay, to give some time for the audience to prepare for some questions. Let me ask one question. So in this scheme, could you distinguish your modular space, I mean the fundamental domain of your modular field, some region which successfully reproduce the observed quark and lepton masses, and the other region which could not produce the realistic quark and lepton masses?
Well, at least from the point of view which we have done from the top down, we are not yet so far that we have models which are solving all the problems. We have the same situation that fitting the lepton sector is easier than the quark sector from the point of view. And the thing, of course, is that maybe I have made that a bit too simple. If you have, of course, the traditional flavor symmetry, which is delta 54, which we have here, this is not broken by the modulus. Yeah. So there we also have to introduce flavon fields in order to break delta 54 down to a smaller symmetry. So we, in the explicit discussion of the flavored symmetry, we are not yet that far. In the sense that we have completely satisfactory fits. That partially comes from the fact that, you see, in the bottom-up prediction, life is easier because, for example, when you choose the automorphy factors carefully enough, you increase the symmetries, so that forbids certain terms which you do not like. And so this is what is known as the shaping symmetries. And these shaping symmetries in the bottom-up approach, you can choose them by choosing the modular weights very carefully. We cannot do that because they, in the string theory, which we had here before, they are fixed. They are -2/3 and -5/3 in our case, and there's no choice. There's not a different choice we have. So we are more restricted, and I think the explicit construction of a flavor fit is we have not yet done. So the first step for us would be just to scan the literature of bottom up and see what is feasible and what is not feasible at this point. More work needs to be done.
Okay, one more question. So these very interesting, structures for the, flavor and CP, is it the particular feature of the orbifold compactification of heterotic string theory, or you think this could be more generic, or you can have similar structure or similar, scheme in other type of string models like deep blend models? Or
yeah, no, I think to see all this CP, I guess, is very generic, and that's probably you long time wrote a paper about CP as a discrete gauge symmetry in string theory. So you see this CP, which we have here, comes from the fact that you have the modulus going to -m bar of the modulus. This is so this is typically what in string theory has been considered even in the 6-dimensional compactification. So this is pretty generic. Now the question of the other modular flavor symmetry, of course, that depends on the group. Of course, we have a 6-dimensional compactification, but typically these symmetries, when you want to have, let's say, a discrete symmetry, it might only be realized at, let's say, a torus, a kind of a subsector of the theory, and so this is pretty clear in the orbifolds. For example, in the Z3 orbifolds, which had been discussed by Ramos Sanchez and his people, there was one of the complex extra dimensions which had a delta 54 symmetry, and in the others it was broken. Now, a similar situation you could also get when you look at Calabi-Yau. When you have Calabi-Yau and you have an elliptic vibration in these compactifications, and many of the Calabi-Yaus have elliptic vibrations, then for these elliptic vibrations, you have also this SL2Z structure, and you could fit that into this picture. So in that sense, I think this is not just confined to, let's say, the orbifold construction. But of course, in the orbifold constructions, typically the symmetries are somewhat bigger. For example, this delta 54 would, of course, be broken in some way if we start blowing up the orbifold.
Okay, thank you very much. Is there any other questions? Seems not. Okay, then let's thank the speaker again. So let's move to the next talk. Timo, could you upload your talk file and share the screen?
Yes. Okay, can you see?
The next speaker is the Timo Weigand and from Hamburg, and he will speak on the quantum gravity conjectures in string theory. Okay, please.
Yeah, thank you very much, Kiwan, for the introduction and for the kind invitation to speak at this conference, and for the opportunity to review some work with Songju Li, Wolfgang Lerche, and Guglielmo Lockhart on quantum gravity conjectures in string theory, further work with Daniel Klever, Max Wiesner. And then the second half of the talk, I will be discussing upcoming work with Songju Li and Wolfgang Lerche. So the general context of this talk is the Swampland program. And as you probably all know, the Swampland program tries to distinguish between two classes of effective field theory, namely, on the one hand, the set of those effective field theories which are well defined as a quantum field theory, anomaly free and everything, but which nonetheless cannot come as the effective field theory of a consistent quantum gravity theory. These theories are called the Swampland. And distinguish this, on the other hand, from the so-called landscape of effective field theories which are fully consistent even when we couple gravity in at the quantum level. As you also know, initiated by Kumru and Waffer some years ago already, a number of proposals or conjectures have been put forward in the literature to distinguish between these two types of theories. And while it would certainly fill one or maybe several seminars to give an overview of all the arguments, I at least want to highlight two types of arguments to give you a general idea of the kind of reasoning. So one favorite kind of type of argument uses the so-called completeness hypothesis to constrain effective field theories in the presence of quantum gravity. The completeness hypothesis claims that in a quantum gravity theory, if you have a charge lattice, because you have gauge degrees of freedom, for example, then every element in this charge lattice or in this weight lattice more generally should actually be realized as a physical state. And in some cases, this can include objects which can be higher dimensional, for example, in 6 dimensions that were just mentioned in the talk before. These could be strings, or in even higher dimensional quantum gravity theories, this could also be branes, which therefore must be in the spectrum of the quantum gravity, and which have certain consistency conditions on their own. And these consistency conditions could be violated in a random field theory that I just write down. So the fact that we're in gravity and not in field theory implies the existence of these extra probe objects, strings or branes or higher dimensional objects, whose consistency would then lead to extra constraints on the effective field theory as such. The second type of argument, and this is more in the spirit of what we're going to discuss in this talk, is the idea that in quantum gravity, the cutoff of the theory can be, in certain regimes at least, much lower, parametrically lower than the naive cutoff that one would think. In particular, it is claimed that if we go to infinite distances, and these are typically regions where the gauge coupling, say, in a theory becomes very small, that then the cutoff of the theory is parametrically lowered from, say, the Planck scale, the maximum possible cutoff, to something like GM Mills times the Planck scale, which could be very, very low. And this can also render certain theories into the swampland, put them into the swampland, if they are defined as quantum field theories with a cutoff which is just below the Planck scale. So for example, if you start with a QFT, which is perfectly well defined, up to a certain cutoff lambda QFT, which sits below the Planck scale, you would think that this QFT is absolutely safe. However, in the presence of gravity, if we take the gauge coupling to be very small, then it's claimed that there should arise an infinite tower of states, and the renormalization effect of this infinite tower of states is essentially to lower the cutoff from the maximum possible value of the cutoff from M Planck to something which can be parametrically below even the cutoff of the QFT. And in this case, the original QFT, without these extra states taken into account, would be in the swampland. These and further ideas of this type have by now led to an ever-growing web of quantum gravity or swampland conjectures. What I'm showing here is just a small sub-web of this ever-growing web. What's important is to note that the different ideas, even though in general conjectural, nonetheless are related to one another in a logical way. Certain conjectures follow from others, and one of the important questions is to find out which, if any, of the conjectures is maybe the most fundamental one from which many aspects can follow. If you're not familiar with this and would like to read more, I invite you to take a look at these excellent reviews listed down here. In this talk, I'm mostly going to focus on the Swampland distance conjecture, which in many respects lies at the center of this web of conjectures, and which is related in an interesting way to some of the other ideas. So what does the Swampland distance conjecture state? Take a quantum gravity theory, and suppose the theory has certain dimensionless couplings. Then in quantum gravity in general, that would be conjecture number 0, every dimensionless coupling should be the vacuum expectation value of a modulus field of a dynamical scalar. This is something that we, of course, are all familiar with from string theory, but which is supposed to hold more generally as a quantum gravity conjecture. So we have a moduli space, and the Swampland distance conjecture claims that such a moduli space in quantum gravity must always be non-compact. In other words, it must always be possible to find directions in the moduli space which have infinite distance with respect to the moduli space metric. So this would be the metric of the kinetic terms in your Lagrangian, say. And furthermore, if you look at if you traverse the moduli space along such an infinite distance, if you go to one of these boundary points at infinite distance, then what should happen is that a tower of states becomes light exponentially fast in the distance. So if you go a distance delta phi, which is larger than m Planck, then you would get down a tower of infinitely many states, which become exponentially light. And these infinitely many states would be precisely those which are responsible for lowering the cutoff of the theory, at least in this limit. In order to apply this conjecture to actual phenomenological questions, we need to know much more of this. In particular, we first need to know how fast this exponential decay would appear. So this is the question about the constant c that appears here in the exponent. And according to the refined Swampland conjecture, this number should always be of order 1. Another question is, how long does it take until we reach the region where the exponential decay starts? This would be these red regions. How much space do I have in moduli space before that? And the refined Swampland conjecture always also claims that this region, the blue region, before the exponential offset starts, is also essentially order 1 in phi. This is a conjecture, and all these 3 aspects of the conjecture, the existence of the tower, the value of c, and also the volume of this region before onset of the exponential decay, can be tested, of course, in string theory, and have been tested. And there are numerous tests or proofs in a certain framework of the statement in various corners of the string landscape, beginning with type 2 compactifications to 4 dimensions with n equal 2, first in the complex structure moduli space by these authors. And we will also report on further tests. So the Swampland distance conjecture is important because it tells us that at infinite distance, the theory changes to the extent that an infinite tower of states becomes relevant. But as such, it does not yet tell us what exactly happens at infinite distance. So in other words, what is the origin, what is the nature of the towers of state at infinite distance? And what is the physics implied by them at the asymptotic boundary? So do we just get a complete mess with infinitely many states and everything is lost and we don't know anymore what to do? Or can we say more about what happens actually on the boundaries of field space? And this is a question that I find very interesting, because from experience with, for example, field theories, gauge theories, quantum gauge theories, we know that in principle, a lot of interesting physics can be discovered by looking at boundary points of the moduli space. For example, in quantum field theory without gravity, we all know from experience that the boundaries of moduli space at finite distance include a lot of interesting new phenomena. For example, they can include completely new sets of theories, strongly coupled conformal field theories, for instance, in 6 dimensions, the famous n equal 1,0 SCFTs, or 4-dimensional strongly coupled theories, which do not even have a Lagrangian description. So in view of this experience, it's natural and important to wonder if there are also new phases of quantum gravity sitting at the boundaries now at infinite distance in moduli space for us. Or if those fields, if these regions at the infinite distance boundary leads back to something that we already know by duality. So in particular, we can ask if the infinite distance regime can still describe by an effective field theory, maybe not by the original one, but by a different one. And these questions are addressed or attempted to address in the emergent string conjecture, which to some extent is a refinement of the Swampland distance conjecture. The emergent string conjecture claims that at infinite distance, always in quantum gravity, one of the following two happens. Either at infinite distance, the theory essentially reduces to a weakly coupled string theory. This means that the tower of infinite states comes from some dual, some other type of string, which at infinite distance becomes weakly coupled and asymptotically tensionless compared to the Planck scale. So the tower of excitations is well defined because we have a weakly coupled fundamental string, and we have infinite, they are weakly, and their interactions are known. So we have a weakly coupled string theory. Or if this does not happen, then the infinite tower should be interpreted as a dual Kaluza-Klein tower, or maybe several dual Kaluza-Klein excitations. So put differently, all the infinite distance limits, which do not change the effective number of dimensions, say the infinite distance limits, which take us to the boundary of quantum gravity, but remaining, say, in 4 dimensions, all those limits should be weakly coupled string theories. That is at least the conjecture and the claim. And while hard to prove, of course, in full generality of quantum gravity, this is, at least it has been confirmed so far in highly non-trivial, also non-perturbative setups within string or M theory. It has been shown in a number of different corners of the landscape that if you go to infinite distance and if you do not change the number of dimensions, then you indeed find a unique, emergent, fundamental, critical string appearing. And the uniqueness and criticality of the string both are a consequence of the quantum geometry of the string compactifications. This was addressed first in F and M theory compactifications to 6 and 5 dimensions, also to 4 dimensions. It holds also in compactifications of type 2 in the 4D n equal 2 setup, including the intricate structure of hypermultiplets and the quantum corrections. It holds in compactifications of M theory and has been observed there. And in the context of 4D n equal 1, it even survives the leading, at least, n equal 1 quantum corrections. So in the remainder of this talk, I would like to first give you a brief review of the emergent string conjecture and how it arises in the Kähler moduli space of a particular theory. I'll take as our laboratory the 4D n equal 1 F theory compactification, because this is a theory in 4 dimensions and it has n equal 1 supersymmetry, so the least amount of supersymmetry that we have before going to 0. And I'll discuss it in the closed string sector in Kähler moduli space. And then in the second part of the talk, I would like to switch gears and try to ask if such infinite distance limits exist also in brane moduli spaces, something that has not been discussed before. And I'll also consider this in the F theory context. So in the first part of the talk, all we need to know about F theory is that it's a compactification with branes, with 7 branes, to 4 dimensions. The 4-dimensional, the space in which we compactify is a Kähler space. It's a 3 complex dimensional space, B3. And on this space, we also have 7 branes in the picture. Details for now are not important. And this is in fact the base of an elliptic vibration, of elliptic fourfold, but also this is not crucial for us at the moment. The only thing that is crucial is that gravity is dynamical as long as we keep the space to be compact. And the Planck scale with respect to the string scale is set, of course, by the volume of the compactification space in the Einstein frame. And likewise, the inverse gauge coupling squared is set by the volume of the cycles wrapped by the 7 branes. In this case, this would be complex 2 cycles or real 4 cycles. So we are now interested in testing this conjecture, the emergent string conjecture, in a Kähler moduli space, namely in the closed string or moduli space associated with the volume moduli. So we look at situations in which one or several of the Kähler of the volume moduli become infinite. And we ask what happens in those limits. What type of degenerations occur for the compactification space, the 3 complex dimensional space. This is actually a technically involved classification that has to be done. And I'm just reporting this cartoon from the result. Namely, what happens is the following. First of all, the overall space, if we take one or several of the volume moduli to infinite, the entire space can become infinitely large. We can divide out by this homogeneous rescaling. And what remains then is one of the following 3 options. Either the space on which we compactified this B3 space has the form of a sphere fibered over 2 complex dimensional space. This is a rational vibration or P1 vibration. And the volume of the sphere becomes very small relative to the volume of the space. In fact, it goes to 0 while the volume of the base goes to infinity. So there is such shrinking fiber, and it's the unique, fastest shrinking, non-contractible curve in the setup. Possibility 2 would be the same setup, just that the shrinking curve is not the P1, is not a sphere, but a torus fibering here. So this is an elliptic vibration, but it's not the elliptic vibration of F theory, it's on the base. Or none of the 2. So there does not exist any unique, fastest shrinking T2 or P1 fiber in the geometry. This could be because the geometry does not admit for such vibrations in the first place, or it does, and some of these fibers, different such fibers exist, they shrink at the same rate. So there does not exist a unique fastest shrinking T2 or P1 fiber. It's the complement to these 2 statements. So that's a purely geometric statement. What is now the resulting physics? We consider type 2b, or F theory compactified on the space, in a situation where the volume of, say, the fiber here goes to 0 on the base. Now what happens is that we can consider a D3 brane wrapping this curve. And this D3 brane now corresponds to a string in 4 dimensions. And as the volume of this curve becomes very small, this string becomes asymptotically tensionless. This string is in fact a solitonic heterotic string. This you can show. This is a consequence of this being a P1 fiber in F theory. So at infinite distance, as this volume here becomes very small, we recover an emergent, asymptotically tensionless, and therefore also weakly coupled heterotic string. And the excitations of this string furnish the infinite tower of states predicted by the Swampland distance conjecture. This is possibility 1, if we have this P1 fiber. Possibility 2 would be to have the T2 fiber, then the string that we get is just a type 2 string, complicated one, but not a heterotic string. Or, and that's the important statement, all other limits are necessarily decompactification limits. So in all other situations, there's a KK tower which goes to 0 faster than any other particle tower in the theory. So the theory effectively decompactifies. This picture, in fact, survives quantum corrections, at least the leading alpha primed corrections, perturbative alpha prime corrections in 4D n=1 theory. And it is interesting because it allows us to derive from it, at least at infinite distance, the weak gravity conjecture. The weak gravity conjecture states that in every theory of quantum gravity, there should exist in its lattice version, a lattice or sublattice of states whose charge to mass ratio is bigger than the charge to mass ratio of any extremal black hole in the theory. And indeed, with this input, you can show that this happens. More precisely, if we consider the gauge theories on a 7 brane, then whenever it is possible to take the limit of the gauge coupling to be 0 of that 7 brane, then you are in a situation where you have an emergent heterotic string appearing, which is tensionless and whose excitations therefore furnishes the states in fact, a sublattice of states which indeed satisfy this relation. So the string emergence helps us to actually prove the weak gravity conjecture, at least in the limit where G-Young-Mills goes to 0 in the framework of F-theory. As I said, this holds not only strictly asymptotically where G-Young-Mills goes to 0, but also survives at least the leading quantum corrections, meaning the one-loop corrections to the gauge coupling, and also, according to a proposal, mass renormalization effects on the string states. So this concludes the review of how to show the emergent string conjecture in Kähler moduli space in a prototypical framework here, F-theory to four dimensions with n equal 1. So in the remainder of the talk, I would like to ask a slightly different question. Namely, we would like to understand also possible infinite distance limits in the open string or brane moduli case. So is it also possible to have infinite distance limits for open moduli or for brane moduli? So naively, in string theory, you would expect that the open string moduli space should be compact. Why? Because the open string moduli space is the moduli space of branes on a compact space. So naively, you would think that this is therefore automatically compact space. Or group theoretically, this moduli space corresponds to the Coulomb and Higgs branches of your gauge theories, which are also supposed to be compact. In this work, we are going to address this question again within F-theory for definiteness as our laboratory. And in fact, in the simplest type of F-theory compactified to 8 dimensions. And the main message is this one. The main message is that infinite distance directions in the 7-brane moduli space do exist. And they describe directions, the resulting directions describe enhancements from a Lie algebra to a loop algebra. And the physics interpretation is that of an effective dual decompactification limit. So the emergent string conjecture is again satisfied to the extent that the tower of states that one finds, and which group theoretically has to do with the emergence of a loop algebra rather than a Lie algebra, that this tower of states indeed furnishes a dual KK tower. So this was the main statement, and now I just need to make this concrete. And for this, we need to, unfortunately, dig a little bit deeper into the workings of F-theory. So F-theory, that's type 2B theory with 7 branes. As you know, in type 2B theory, there are 2 types of strings. There's the F1 string and the D1 string, and a general string which has charge P with respect to F1 and charge Q with respect to D1 is a PQ string. Such a PQ string can end on the PQ7 brane. And if you transport a general, say, RS string around such a PQ7 brane, then the charges of the string change by a monodromy, and the monodromy is an SL2Z matrix that depends on the PQ charges of the brane. The details are not important. The important is this picture to have in mind. We compactify F-theory to 8 dimensions on a P1. We have 7 branes. These are at points on this P1 and fill the remaining 8 dimensions. And as you encircle such a 7 brane, then you have these monodromy transformations that change the asymptotic the charges of the strings that you transport around. All this leads to the construction of the usual ADE Lie algebras in F-theory in the following way. You can stack together different types of branes depending on their PQ labels in order to reproduce the known ADE classification of branes for the 8-dimensional compactification. So for example, if you want an E-type series, E5, E6, E7, E8, then you have to stack together this type of branes of different type of monodromy, and it suffices to go to a basis where we have 3 types of branes of this form. So this is how one gets usual Lie algebras in F-theory. However, that's not all. As was shown in a series of beautiful papers by De Wolf et al., just based on the monodromies of the 7 branes, one finds that one can also look at configurations of branes that describe affine enhancements of the Lie algebra to affine or Kac-Moody algebras. More precisely, consider the En series, so E6, E7, E8, for example. Then these authors showed that if you take another brane of PQ labels 3, 1, and place them on top of the En brane stack, you enhance the Lie algebra En to the affine Lie algebra En, which in fact is a loop algebra. More generally, it's even a Kac-Moody algebra. How do you see this? The authors show that if you consider the monodromy action around this pair of, say, En branes and this extra brane, then the monodromy takes this form, this characteristic upper triangular form here. Such a monodromy action obviously has an eigenvalue. So a string delta with these charges, a 1-0 string essentially, once transported around will go to itself. So you can transport such a string around such a configuration. A string encircling the total configuration gives rise to a well-defined BPS state, and this becomes massless once the two branes, the En stack and the X brane come together. And these massless states extend or enhance the Lie algebra En to the affine Lie algebra het En. More precisely, the state delta is associated with a so-called imaginary simple root, which has the property that it's group theoretically delta dot delta is 0, and it's also has 0 inner product in root space with the roots of the original E8. And these two properties are precisely what it takes to have an affine enhancement. So you cannot do all possible affinizations in this way, but you can do it for the entire E series, so for E6, E7, E8, but also for E5, which is D5, E4, which is A4, and also the sublier, some lower lying examples, including E0, which would be just the affine enhancement without any gauge symmetry to start with. This would be the rank 1 enhancement. What about rank 2 enhancements? The authors show that there is a multitude of possible rank 2 enhancements. Relevant for us is the one where we start from the loop algebra het E8. This was the first thing, what we did on the page before. And then if we also include a second brane, in fact an A brane, we get a second type of string junction that can encircle. So if we put everything together, we get two types of junctions, delta 1 and delta 2, which are both massless and orthogonal on one another and on themselves. So this is the enhancement to the loop algebra of E8. And this is in fact the type of further enhancement that we have to consider. So this analysis by de Wolf et al. Discusses all this in detail from the monodromy aspect. What it doesn't explain is the physics interpretation, which loop enhancements can occur, and how is all this realized on elliptic K3s in terms of actual Weierstrass models of F theory. So let me very briefly address these points. Namely, first, the physics interpretation. This imaginary root delta that we get in this way gives rise to a BPS state. You can, in fact, take n copies of the state, and in this way, you still get a BPS state. This means you find an entire tower of BPS states, one BPS state per imaginary root. So our interpretation is that these affine and loop enhancements, which were studied by de Wolf et al., signal indeed an infinite distance degeneration in the open string moduli space, broadly interpreted, of a 8D-dimensional F theory. And our interpretation of the BPS towers is that these BPS towers are the Kaluza-Klein towers associated with a dual decompactification along a circle. More precisely, if you have an enhancement to a hat En for n smaller or equal to 8, you find one tower, and this corresponds to a decompactification along one circle to 9 dimensions. If you consider the special double loop enhancement to hat E9, you find two towers. So this is a dual decompactification from 8D to 10 dimensions. Our interpretation why these should be viewed as KK modes is backed up by an analysis of the heterotic dual, which I will provide in a second. But it's also clear already from the fact that these group theoretically, these various junctions are orthogonal on themselves and everything else. So if you look at the resulting BPS states that you get by taking all possible linear combinations, these look precisely like, of course, a KK tower of the original 8-dimensional theory. So what is also not clear a priori is how in detail one explains these possible enhancements in the language of elliptic vibrations. The compactification of F theory on a rational curve P1 to 8 dimensions is equivalently described by F theory on a K3 surface. By this, we just take into account also the elliptic fiber, whose complex structure is the exodilaton. What's important for us is that these models have a well-known description as a Weierstrass model in terms of two characteristic functions, F and G. And this combination, the discriminant of these functions F and G, tell us where the 7 branes sit. So this is for us just a useful way to keep track of the possible consistent configurations of 7 branes. And as is very well known, the finite enhancement, the finite algebra enhancements are in fact in one-to-one correspondence with the classification of possible singularities of the elliptic fiber on such K3 surfaces, namely to each of these algebras that we described before in terms of the stacks of coincident branes, one can associate certain vanishing orders for these functions f, g, and delta, and the Kodaira-Narain list gives a one-to-one correspondence between these two sides. What's important for us is that this list famously stops at 4, 6, and 12. These are non-Kodaira or non-minimal singularities, and in codimension 1 at least, the slogan is typically that one should not go there and not discuss these. And the main point is that these non-minimal fibers, the non-Kodaira type fibers, indeed correspond to these loop enhancements, i.e. the infinite distance enhancements in open string moduli space.
3 minutes.
Please.
3 minutes?
3 minutes.
Okay.
Very good. Yes, 3 minutes. Thank you. So if we enhance to order 4, 6, or higher, then these are precisely degenerations at infinite distance, which give rise to these affine algebras and hence to dual decompactification limits. In fact, this can be done technically. One knows how to deal with these non-Kodaira type enhancements in codimension 1. One has to blow up the base in a certain way. This was discussed in great detail already in the literature. But what we observe is that after the blow up, this series of possible affine enhancements and hence types of decompactification limits can be read off from the Weierstrass orders after the decompactification in a specific way. I don't have much more time. I just want to show you 2 cartoons how this is done. For a particular Weierstrass model, say a Weierstrass model that gives gauge group E7 times E8 in 8 dimensions, we can easily engineer 4, 6, 12 or other non-Kodaira types by taking some of the coordinates to 0, here for instance in this way. If we do this, we have to perform this series of blow-ups. So the base of this elliptic vibration now becomes the set of intersecting curves. And the monodromies along the endpoints, the DP9 surfaces, in fact, at the endpoints, these monodromies coincide with the monodromies of the affine enhancements. For example, if one does it in this particular way for otherwise generic coordinates, one finds a decompactification to 10 dimensions. This is the famous Kulikov type 2 degeneration of K3 for the experts. But we can go systematically much beyond this. We can also look at situations where we only end up with enhancements of type het En for n smaller 9, corresponding to decompactifications, for example, from 8 to 9 dimensions, and in fact, understand the resulting patterns in a very algorithmic way. The very last point I want to make is why this actually corresponds to a decompactification limit. This we prove by considering the match with a dual heterotic string on a dual torus. F theory in 8 dimensions is dual to heterotic string on the torus T2. As we already learned in Hans Peter's talk, just mentioned it, is that in situations with Wilson lines, the structure of this heterotic torus is in fact, of this heterotic theory is in fact described by certain Siegel modular forms. One can map the Weierstrass function to certain Siegel modular forms. One can look at the degeneration of these Siegel modular forms in the limit of the Weierstrass function in the Weierstrass model, and indeed show that these limits correspond to decompactification limits on the heterotic side. So, for example, the type 2 situations with het E9s, the 10-dimensional limit, this would be a situation where only the complex structure moduli goes to infinity on the dual side. Kähler modulus stays finite, whereas, so this means one cycle goes to infinite radius, the other one stays finite. And one can also discover in this way the 9-dimensional limits. So this is all technically well understood and can be made quite precise. Let me summarize. In this talk, we found further evidence for the emergent string conjecture, which states that every infinite distance limit in quantum gravity is either a tensionless fundamental string limit or a decompactification limit. So the key challenge is to argue that whenever you have an infinite distance limit without a string, that it really describes a dual decompactification. This was previously confirmed in various setups in the Kähler moduli space. In this upcoming work, we're discussing it in the open string or brane moduli sector in F-theory. We show that the infinite distance directions correspond to affine or loop enhancements. They are classified by monodromy, and we show that precisely these cases can also occur from the perspective of the geometry. The slogan is that affine algebras, the imaginary roots of these affine algebras, lead to BPS towers, which signal a dual decompactification to 10 dimensions in agreement with the heterotic dual. And by performing this analysis systematically, one can in fact reproduce, for example, the possible types of gauge algebras in 9 dimensions after such a decompactification step, in agreement with the classification put forward in this recent paper by Font et al. Before I thank you for your attention, let me in particular, since I have the honor of being the last speaker, say a big thank you to the organizers of this conference for their hard work and their successful work. I know from firsthand, since I was in close contact with one of the organizers, that this is a lot of work and you've put a lot of efforts into this. Thank you very much for this great service to the community. And thank you all for your attention.
Okay, thank you very much, Timo. And also thanks a lot for the very nice and excellent talks. So this is the time for questions. I found one question in Q&A. Could you read this Q&A, Timo? From Owen Colgain.
Hang on. What do I have to do? Ooh. Can you still see these slides or not? No, sharing is paused. Okay.
So shall I read the questions?
I can read it now.
Okay, okay.
My understanding is that the distance conjecture and Busse bound lead to a derivation of the de Sitter conjecture. Indeed, this is the work by Palti, Shiu, Waffa, and Oguri. Subiasaka et al. Have a 5 sigma statement against Friedman-Robinson-Walker universe. If this fails, then dark energy is no longer guaranteed. Dark energy. This could be constructed as some success for this problem, assuming it's true. Yes. So what is true? I thank you for this comment. It's a very good comment. In particular, I would like maybe to those not familiar with this work, make one comment to the first part. Indeed, the Swampland distance conjecture was used by this work by Shiu et al. To derive the no de Sitter conjecture at infinite distance in moduli space, namely in the part of moduli space where you really go far out and where you have this, this behavior of an exponentially small tower. So this is the region of very weak coupling, and I guess it's even the biggest opponents of the Swampland program would not argue against the statement that at very weak coupling, very far out in moduli space, no actual de Sitter vacua have been found so far in string theory. This is a more drastic version of the Dine-Seiberg problem. Nonetheless, of course, the call is still out what happens in the interior of moduli space. This had to do with this remark at the very beginning, before this onset of exponential tower starts, what is the structure there? And these non-trivial constructions of KKLT and other variants, of course, are precisely in this regime. So the question is probably still out for de Sitter, but indeed, as you point out, the distance conjecture does shed some light on it, at least asymptotically far out.
Any other questions? Well, I have one very naive question. So when you talk about this infinite field distance conjecture, are you talking about the light moduli at the string scale? I mean, you know, that applies for the moduli parametrically rather than the string scale or complete string scale, or suppose that you could stabilize some of the moduli. And
very good.
At much lower scales, then somehow you are confined, you know, because some of the moduli are stabilized, so that you are confined. Some of the moduli are fixed as their vacuum values, while maybe you can still be able to move around the, you know, field directions along the light moduli only.
That's right. So you could either view it like this: if in 4D(n=1) you have stabilized some of the moduli, then first of all, you can go along the remaining directions. That's certainly true. Or you could take the viewpoint, you have stabilized the moduli, so you have a potential. So nonetheless, you could, you know, like in this typical minimal potential, like in KKLT, you could think of going through the potential wall and nonetheless go to the region where you have run away.
Potential wall and okay, they go to the okay, even if okay.
Yes, indeed. And in this regime, it then will still work and still apply even in presence of a potential.
So basically, I mean, you move along over the entire modular sphere, regardless of whether some of the moduli stabilized or not. Okay.
Yes, exactly.
It seems that there is no other questions. Okay, then let's thanks to the team again, and because this is the last session of this PASCOS conference. I also would like to thank all the speakers for the excellent talks, and also all participants for the active participation, and also all the local organizers for this you know, nice organization of the conference. Okay, thank you very much, and I hope that we can see in some future in person in some place, of course also in Korea. Thank you very much.
Thank you.
Okay, bye-bye. Let's close the session.
Bye-bye.